So as we can read on the board, it says spectator and it also has this weird quote. And these both are two different ways to help you remember all the different circle theorems. So we'll see how spectators are used, and then this quote, teachers regret pupils crying at end of school trip. All the these first letters stand for circle theorem. So that's just in the exam, if you know it's a circle theorems question, you're trying to remember them all and work through, oh, which one is it? You can think back to that and tick them off. So our first circle theorem is the T for teachers, or T for tangent, and it is that when you draw any tangent to the circle, so tangent is a straight line that just touches the circle, so let's do another one here, so that's a tangent, just touches the circle, and then you draw a line from the radius to the tangent. This angle here is always 90 degrees. So that's number one. Okay, so circle theorem 2. First of all, I'm going to cross the T out in spectator for tangent, and that's the T in teacher. So now we're on to the R for regret, and the R stands for radii, and the rule is that two radii, so that's a plural of radius, which is a line from the centre to the circumference, form an isosceles triangle. So let's see this. So I'm just going to draw any two radii. That's one. That's two. So if I just connect those together, any two radii form an isosceles triangle. An isosceles triangle means that these two angles here are the same. We also know that all the angles in a triangle add up to 180. And we also know, but it doesn't tell us, normally for an isosceles triangle, it gives you these two lines which indicates the same length, but most of the time on this it doesn't actually tell you that, because you should know that anyway because they're both radiuses, so they have to be the same length. So let's cross out the R in spectator and move on to the next one. So circle theorem 3 is the P for pupils, and that is the perpendicular bisector. So what that means is if we have a chord, which is any line across the circle but that doesn't go through the centre, because if it went through the centre that would be what we know is the diameter. So a chord is any line drawn across the circle, and any line that cuts the chord in two has to go through the centre of a circle. So if I'm cutting this in half, it always has to go through the centre. So then this length here is the same as this length here, because we're cutting in half. Let's just do that again. So I'm just going to draw another chord. Let's draw one here. So any line that cuts that in half has to go through the centre. And that also means then that that is a right angled triangle. Right angled triangle, that is 90 degrees. And so is that, a right angle. And that is the same length as that, because we've cut it in half. So let's cross out the P in spectator for perpendicular bisector and move on to the next one. So our fourth circle theorem I call, which is the C, the cry for crying, or for centre. So this is the one I call centre, and I think this one comes up a lot. I remember it coming up a lot for me, and that is that if this here, that marks the centre by the way, this angle here, but I need to create an angle. So let's say I do this, you have this sort of shape. There. This angle at the centre here is twice as big as this angle here. Looks like kind of a funky shape. That one comes up a lot. Try and remember that one. So that one stands for centre. Okay, so let's cross that off. That's the C in spectator. So our fifth circle theorem is angle, that's the A for at, and that is that the angle in a semicircle is 90 degrees. So first of all, here's roughly the centre again. Let's create a semicircle. So semicircle, that means you have the diameter there. So this is a semicircle. So any triangle I make from these 2 points here, so let's just go like this and like this, that there is 90 degrees. Can do it the other side, so let's just go to here, to there. Bear in mind they're supposed to be straight, 90 degrees. Do another one, why not? It's getting carried away. There, to there, 90 degrees. So that one is angle, so the angle in a semicircle is 90 degrees, and we can cross the A out in spectator. Okay, so the E for N stands for equal for circle theorem 6, and that equal is the angles in the same segment are equal. So first of all, let's draw a segment, which is like a piece of an orange here. And so angles in the same segment are equal. So if I just draw 2 lines coming off there, and I'm going to call that angle A. If I draw another one, let's go from there to there, that angle is also A. So angles in the same segment are equal. We can also do it on the bigger side. That's B. That's B. They're the same size. Let's do... It's quite clever, really. So all those angles are the same size. They are equal. Now let's cross out the E in spectator. Okay, so the O for of here, getting closer to the end, so just keep going. That stands for opposite, and this is rule 7, and it says that opposite angles in a cyclic quadrilateral add up to 180. So this one, out of all of them, I think looks the most different, so it's quite nice to remember. So let's draw a cyclic quadrilateral. So a quadrilateral. So the angles in a quadrilateral. So here are my angles in a quadrilateral, but it's the O for opposite, so the opposite angles add up to 180. And so if A and C, therefore A and C add up to 180, and B and D add up to 180 because they're opposite. And we know then that all the interior angles of a quadrilateral add up to 360, and that makes sense because if those two add up to 180 and those two add up to 180, 180 plus 180 is 360. So that's kind of the most, all the others are kind of be triangle-y, and that one is a quadrilateral. Let's cross out the O in spectator. So now we go on to trip, and then we come back to school. So the T for trip stands for tangents. So the T for teacher stood for tangent. So whenever you see a T, something to do with tangents. And this one states that the tangents from the same point are the same length. So let's pick a point and let's draw some tangents. So tangents from the same point are the same length. So, and we already know from the teachers, the tangent in the circle theorem we did first, that a tangent and a radius, tangent to a radius, that angle here is always 90 degrees, and I don't actually need to write it down because that symbol means 90 degrees. And this was telling us that the tangents from the same point are the same length. So that means this length here is the same as this length here. Also, if we think about it, we can split this here. And here we have two congruent triangles, triangle 1 is exactly the same as triangle 2. Almost there, just one left. Okay, so let's cross out the T in spectator. So the S in school stands for S here, which I'm saying is segment, and this is the alternate segment theorem. This one I would say is probably the hardest. So what it is saying is, if I just draw a sketch, I've got what this one states is the angle between the tangent and the chord. So this is a chord, a line, but it doesn't go through the centre. So this angle here, which I'm going to call B, is always equal to the angle in the opposite segment. Okay, so this is a segment, and this angle here is always equal to this angle here. So this one's always a bit harder to spot. So we can cross off the S in spectator, and there we go. We've gone through all the 9 theorems, so I hope that just helps you remember them. And now we're going to go on to some exam questions. Okay, so this is exam question 1. So here we have a circle, and then I've labelled the angles it's given you, and it's asking you find the angle ACD and explain why, so like which circle theorem you've used. So first thing to do is literally which angle is actually asking me for. So you go A, C, D, and it's the angle in the middle. So A, C, D. This is the angle we are after. And then you can either go through every single circle theorem, but this one actually applies to the equal one, so that the angles in the same segment are equal. So if we think about it, we can draw. So this one was number 6, and it was the one that looked like this. So as you can see, B. So this angle here is the same as this angle here, because it's in the same segment. So the answer to that is 54. Okay, so this is exam question 2, and it's given us what I put on there. So it's just given us that angle at the centre, 168, and it says find angle ABC and ADC. So first ABC, so first let's identify which angle we are looking for. ABC is the one in the middle, so we want this angle here, and we can run through all the rules. So it's not a teacher's tangent one, the R radii one, 2 radii form an isosceles triangle. Don't think it's that, because the 2 radii here aren't forming a triangle. Perpendicular bisector of a chord, no, that's not happening. And then C, the crying, so centre, so that's the angle at the centre is twice the angle at the circumference. And yes, bingo, that looks like the one we want. So this angle here at the centre is twice the angle at the circumference. So if we look back at this one example, it's this one here. So it looks very similar, this bit here. So we know that this angle here is half the size of the one at the centre. So ABC is 84 degrees. Okay, I'm going to wipe that away. We now know this. What about ADC? What about this angle here? So there are 2 ways we could approach this, and one is the quadrilateral rule. So here we have a quadrilateral, and that is the O. The opposite angles in a cyclic quadrilateral add up to 180. So we know that the opposite angles B and D equal 180, and we know B now, 84 plus 8 equals 180. So D is 180 minus 84, which is 96 degrees. So that way was using that circle theorem, the opposite angles in a cyclic quadrilateral add up to 180, and if we got rid of this inner bit here, it would look like that. So B and D are opposite, add up to 180. The other approach would be using this one like before, but we don't have this is the angle we're looking for. So the angle at the centre would be this one this time. And we can work out this angle by doing 360 minus 168. So 360 minus 168, which is 192 degrees. We know this is 192 degrees. Then we can use this same rule here. Angle at the centre is twice the angle at the circumference. So 192 divided by 2 is 96 again. So there are two ways we could approach that question. So our final exam question is here, and our first thing it asks us is find A, B, D and Y. So first of all, what is A, B, D? So A, B, D, so we're looking for this angle here. So using the first circle theorem, the T, the tangent one, so this, because it's coming from the centre, this is a radius, and we know that the angle between the tangent and the radius, first rule, this looks a bit massive, is 90 degrees. We already know that's 35, so ABD is going to equal 90, the 90 degrees, minus this 35 degrees, because we want this red bit here. And that is 55 degrees. So instead of a question mark, we can write 55 degrees. Second part, find Deb. Where's Deb? D-E-B. So first identify what that is. D-E-B. That's this angle here. So this to me looks a lot like the alternate segment theorem, because I found it's kind of made me find this angle, like the key angle I need, and it is in fact that one. So this angle and this angle are the same from the school, the alternating segment theorem. So Deb is also 55 degrees.